Welcome all of you to my YouTube channel. In this video, we will discuss about the incompressible viscous flow in pipes. So I will divide this chapter into three parts. In part 1, we will discuss about the basics, the fundamentals of a pipe flow problem. So pipe flow means it is basically internal flow of different cross sections. The pipe or duct may be of circular cross section, the duct may be of rectangular cross section, maybe triangular cross section. And in this video we will discuss about the fundamentals like the laminar flow, the turbulent flow, the entrance region, the fully developed region, how the flow development takes place. So all these basic things we will discuss for a pipe flow. But the flow must be viscous and incompressible. Basically we will focus on these two conditions for a flow inside a pipe. So internal flow means the flow is completely bounded by the solid surface. Solid surface means the wall of the pipe or duct. Examples are the flow may be through pipes, the flow may be through nozzles, the flow may be through diffusers, the sudden contractions, sudden expansions. So all this comes under the internal flow, but basically we will deal with the flow through pipes. The flow regime may be laminar or turbulent is very important because the physics of laminar flow is completely different than the physics of the turbulent flow, and also the entrance region and the fully developed region also comes into picture when the flow takes place inside a pipe. So the entrance region, the theories for entrance region is also completely different than the theories for fully developed region. So all these things we will discuss for a pipe flow. So already we discussed that pipe flow means the flow is completely filling the pipe. So this is the pipe flow 1, and mainly the pressure gradients along the pipe is the main driving force, because in case of a pipe flow the pressure at the inlet is higher than the pressure at the outlet. That gives rise to a pressure gradient along the direction of the flow. And this 2 is the open channel flow, the flows without completely filling the pipe. That means you see there is some gap between the free surface and the top wall of the pipe. So that is the open channel flow, and the gravity is the driving force. Generally there is some slope along the direction of the flow, so the gravity helps in the flow. Basically we mechanical people mostly encounter the pipe flow problems, and this open channel flow generally the civil people mostly discuss this open channel flow. Now the very important topic in case of the pipe flow is whether the flow is laminar or turbulent flow. Turbulent flow. First we have to know whether the flow is laminar, the flow is turbulent. Then only we can proceed with the further analysis of the pipe flow. So Osborne Reynolds is a British scientist, mathematician. He is the first person to distinguish the difference between these classifications, whether the flow is laminar or the flow is turbulent, by his classic experiment on fluid mechanics. In 1883 he did this experiment, very simple experiment, but it is very famous experiment. Even fluid mechanics lab also we perform this experiment, Reynolds experiment we call it. So what he did, he take a transparent material for the pipe so that we can see what happens inside the pipe, and some water is flowing inside the pipe, and he use a color dye container, and the dye was injected to the water flow at different velocities. So he go on increasing the velocity of the flow. So velocity means increasing the flow rate basically, because the flow rate is the product of velocity and the cross sectional area. So by increasing the flow rate, he observed different behavior like this. So at small flow rates, so the die was moving along a straight line. So there was no change of the position of the die. But when he increased the flow rate, he observed that for some portion the die was straight line, then it was deviating from the straight line, and at very high flow rates he observed completely a chaotic motion of the die. So sometimes the die was moving upside, sometimes the die was moving downside, completely in a haphazard manner. So in different behaviors he got by going on increasing the flow rate inside a pipe. So he classified the flow as laminar flow, transitional flow, and turbulent flow. In laminar flow, the die was moving along the straight line, no change of its position. That means it is not mixing with the surrounding fluids. And in case of a turbulent flow, the die was haphazardly, chaotic manner moving and mixing with the main flow, that is the water flow. So this is the turbulent flow. So this is the classic experiment done by Reynolds, which gives the idea of laminar flow and turbulent flow. So he also observed the time dependence of the fluid velocity. So at a particular point, if we will observe the velocity with respect to time, so velocity versus time. So in case of a laminar flow, there is no change of the velocity with respect to time. But in case of a transitional flow, so some portion for some time it remains constant, then it's little deviates, changes, then again remains constant. But in case of a turbulent flow, the velocity is completely changing with respect to time. So completely randomly it's changing. Sometimes less, sometimes a little more. So randomly velocity variation with respect to time in case of a turbulent flow. So generally in case of a solving a fluid mechanics problem, how to classify the flow as laminar or turbulent. So Reynolds concluded from his experiments that if Reynolds number, he defined a number, Reynolds number is rho density into average velocity into d diameter of the pipe by mu, that is the dynamic viscosity. It is the non-dimensional number, Reynolds number. If Reynolds number is less than 2100, then the flow is laminar. But if the Reynolds number is more than 4000, the flow becomes turbulent. And in between these two values, the flow is transitional. So now easily we can say whether the flow is laminar flow or turbulent flow. Now what is entrance region and fully developed region? So any fluid flowing in a pipe had to enter the pipe at some location. So the region of flow near where the fluid enters the pipe is termed the entrance region or developing flow region. So at the entrance, suppose this is the inlet to the pipe, so the flow enters with uniform velocity. The velocity profile do not change. It is the same at the wall, also to the same along the center line. So along the center line at the wall, it remains the same. So when the flow enters inside the pipe, the flow development takes place. Why? Because no slip boundary condition. So at the wall, the velocity becomes 0. So at the wall velocity becomes 0, and along the center velocity becomes maximum. So this phenomena, no slip boundary condition, gives rise to the development of the velocity. So velocity profile changes from the uniform to some profile. Then again after some distance it takes another shape. But after a certain length, so up to this, from the entrance to this position, the velocity profile development takes place. But after this point, along the direction of the flow, the velocity profile do not change. Now this is the velocity profile after this point. So this velocity profile 1, and this is also velocity profile, the same velocity profile. So there is no change of the velocity profile along the axial direction. So the region up to which the velocity profile change takes place, that is known as the entrance region. So velocity profile changes means the acceleration effect is predominant in the entrance region. But what happens after the entrance region? There is no change of the velocity profile till the exit of the pipe. So basically in case of a laminar flow, this fully developed profile is the parabolic profile. So if one is parabolic, profile this is 2, suppose profile 2 is also parabolic. So the flow becomes fully developed because there is no change of the velocity profile after a certain distance from the entrance. So up to the distance from the entrance where the velocity profile changes is known as hydrodynamic entrance region, and after the hydrodynamic entrance region the velocity profile do not change, remains same. So it is the fully developed region. So in case of entrance region, the velocity changes along the axial direction as well as along the radial direction. So basically the flow is 2D, two-dimensional flow. But in the fully developed region, the velocity changes only in the radial direction. Along the axial direction, there is no change of the velocity profile. So that means it is 1D velocity profile. Yeah, it is 1D flow, and this is a 2D flow basically. So why this happens? The fluid typically enters the pipe with a nearly uniform velocity profile. So as the fluid moves through the pipe, the viscous effects cause it to stick to the pipe. I told that the no slip boundary condition happens due to the viscous effects. So the velocity at the wall becomes 0, and the boundary layer in which viscous effects are important. So a boundary layer is also formed. So in my next videos we will discuss in detail what is a boundary layer. So boundary layer means it is a small layer from the wall. So inside that region the viscous effects are very important. So the initial velocity profile changes with the distance along the pipe until the fluid reaches the end of the entrance length. So the boundary layer development takes place. You see, so this is this line is the boundary layer line. Similarly, from the top wall a boundary layer development will take place, and from the bottom wall boundary layer development will take place, and they are meeting at this point. So both the boundary layers are meeting at this point. So after that region the flow becomes a fully developed region. So inside this boundary layer the viscous effect is very important, and outside the boundary layer, so this region is outside the boundary layer and these regions are inside the boundary layer. So inside the boundary layer X, the viscous effects are very important. If the viscous effects are very important, so they will try to modify the velocity profile. And outside the boundary layer, like this circular region, the viscous effects are not important. So the boundary layer has grown in thickness to completely fill the pipe up to this point, and after this point the flow becomes fully developed. So this is related to the growth of the boundary layer, and we will discuss this. So boundary layer also is different in boundary layer phenomena is different laminar flow compared to turbulent flow. So boundary layer in laminar flow, boundary layer growth in turbulent flow, all these things we will discuss separately in a video so that concepts will be more clear. So the viscous effects are of a considerable importance within the boundary layer. So outside of the boundary layer, the viscous effects are negligible. So the shape of the velocity profile in the pipe depends on whether the flow is laminar or turbulent. So the velocity profiles in entrance region as well as in the fully developed region, okay, is different in laminar flow or turbulent flow. In laminar flow, basically in fully developed region we will get parabolic shape velocity profile, and in turbulent flow we will get power law profile for fully developed region in case of a turbulent flow. And we have also empirical relations for the length of the entrance region. So this is the length of the entrance region in case of a laminar flow, non-dimensionalized by the time. So LL is the length of the entrance region divided by the D to make it non-dimensionalized. It is 0.06 RE. So it is a function of Reynolds number, directly proportional. And for a turbulent flow, the entrance non-dimensional entrance length is 4.4 RE to the power 1 by 6. So generally for laminar flow, the entrance region is very high compared to a turbulent flow. So due to mixing, so in case of a turbulent flow, the flow development takes place very rapidly. So that's why the entrance region length is very small compared to a laminar flow in case of a turbulent flow. So once the fluid reaches the end of the entrance region, the flow is simpler to describe because the velocity is a function of only the distance from the pipe center line R. That means in the radial direction. So already I told you. So in the fully developed region, velocity profile is a function of only the radial coordinate. Along x direction, there is no change of the velocity profile. So it is easy to do the analysis for a fully developed region. So that's why in fluid mechanics, we will also try to solve a fluid element using the momentum equation. So there also we will use the different expressions like the expression for the shear force, expression for the velocity, for all these things for the fully developed region, because it's 1D and easy to do the analysis. So now pressure distribution along a pipe. So already I told you in case of a pipe flow, so the driving force is the pressure gradient. So at the inlet x equal to 0, you see the pressure is high compared to the exit. So generally the pipe exits to the atmosphere, then it will be atmospheric pressure. So inlet pressure is high compared to the outlet pressure. So how the velocity varies, and the pressure varies in the entrance region as well as in the fully developed region. So in the entrance region, the variation is not linear because the velocity profile is not same. So velocity profile changes. So that's why acceleration effect, due to acceleration effect, the pressure variation is non-linear in the entrance region. But once the flow becomes fully developed, then the linear variation of the pressure takes place along the length of the pipe. So how can you find out the pressure drop? In this case, if you know the pressure profile, if you know the inlet pressure, if you know the outlet pressure, then the pressure drop is outlet pressure, like P3 minus P1, and you know the P3 is less than P1, so the pressure gradient along the length of the pipe, delta P by dP by dL, suppose along the length of the pipe will be negative. So pressure gradient along the length of the pipe is negative. So del P by del X equal to minus del P by del L is less than 0. And in the fully developed region, del u by del x equal to 0. So there is no variation of the velocity along the length of the pipe. So the relation, okay, for the velocity and the pressure in case of a fully developed flow is del p by del x equal to constant, linear variation of the pressure, and del u by del x equal to 0. There is no variation of the velocity along the flow direction. So now you got some fundamentals and basics how your velocity varies in the entrance region, in the fully developed region, as well as how the pressure varies in the entrance region as well as the fully developed region in case of a pipe flow. So this is all about the basics. So in my next video we will discuss more on this topic.